Hello, my name is Richard VanDok, and together with my co-authors Brian Fuller and Ron Bianco, I'd like to share with you today some of the results we've obtained from 3 VSP surveys acquired in the Permian Basin to support the processing and interpretation of a coincident 3-component 3D survey. Let's start with a brief introduction to the area and the underlying geology. The massive 3-component 3D survey sits in the western portion of the Midland Basin and onto the Central Basin platform. Within the boundary of this survey, we were able to access 3 wells at which we acquired 3 3D VSP surveys. These locations are shown here as red circles. As you can see in the cartoon on the left, the 3 VSPs were located in 3 different geological settings. My co-author Ron Bianco and Bruce Carr and Andrew Lewis from Fairfield shared more details about this unique 3D 3C survey during their presentation in the Acquisition 1 session. With that brief background, let's now look at the general outline of this presentation. I'll step through each of these points and hopefully provide more relevant details as we go. So before we look at the data and the results, it's useful to look at the VSP survey design and the actual data acquisition to give some context to the results we're seeing. This slide shows the pre-survey design work and the expected illumination for each of the wells at the deepest target zone, in this case 12,700 feet. The rainbow outline shows the planned 3D 3C surface program with full fold in the gray region. We used a regular grid of sources surrounding each well, but due to some permitting restrictions, a small portion to the southeast of VSP number 1 was not acquired, and VSP number 3 fell on the northern edge of the survey, so only a half circle of sources was acquired. The use of a large 80-level geophone array contributed to the improved efficiency acquiring these VSPs. Each well utilized 3 array positions covering almost 12,000 feet of the wellbore. This required each source location to be reoccupied 3 times. One key thing to point out here is that the same P-wave sources and sweep parameters were used for both the VSP and the surface seismic program. This allows for a detailed analysis of the far-field source wavelet at various depths. I'll talk more on this a little bit later. Here's a map view of the sources acquired for VSP number 2. Which was the most complete of the 3. The VSP location is shown in the center, and the blue dots are the P-wave vibrator points. The colored 2D lines are the locations of the shearwave vibrators. Only VSPs number 2 and 3 utilize shearwave sources, which were acquired in both an inline and crossline orientation. For each well, a zero offset P-wave source was acquired in order to record a vertically propagating wave field. Zero offset sources were also acquired with the shearwave vibrators at VSPs number 2 and 3. Now let's take a look at these zero offset VSP results. This list shows a basic zero offset VSP flow. Zero offset VSP processing is relatively straightforward, but still provides a significant amount of valuable information. In the next few slides, I'll touch on the key processing steps related to this useful data. This is the zero offset VSP data from well number 2. The horizontal axis is receiver depth and the vertical axis is time. The red arrows at the top show the extent of the 3 separate array settings. Here I've highlighted the downgoing direct P-wave arrivals and a few upgoing reflected P-waves. If you look carefully, you'll notice some small variations in the shape of the downgoing wavelet at each array setting, shown here at the yellow arrows. Keep in mind that there are 3 different sweeps acquired at 3 different times. At this location, very little changed between sweeps with respect to the surface conditions, but you still see a small difference, mostly between the middle and deepest array settings. An important step in the processing and analysis of VSP data is the estimation and correction of the downgoing source wavelet. Here we see the data after application of the inverse source designature filters that effectively collapse the energy into a nice zero-phase wavelet. The 3 panels in the lower left each show 3 traces. The first trace is the estimated downgoing wavelet, the second is the inverse filter, and the third is the filtered output. Note how stable and well behaved the wavelet is after correcting for these small but important source variations. Once we've collapsed and stabilized the wavelet, we now pick the direct arrival times. This may seem like a trivial step, but in fact this one-way time versus depth relationship is one of the most significant benefits of VSP data. We'll come back to this in a little bit. Next, we remove the downgoing energy and then correct to two-way time, which flattens the reflected energy for subsequent stacking. I've marked a few recognizable formation tops on this image for reference. As mentioned earlier, these reflections are what will ultimately be imaged, both for the zero offset VSP and the 3D VSP. But before we stack these data, we apply what are commonly called corridor mutes. By excluding the energy coming in at later times, we can effectively isolate only the primary reflection energy and remove the influence of later arriving multiples and noise. This slide shows the application of these mutes and the final corridor stack on the right, with repeated traces just for display. This stack trace can be considered a primary-only reflectivity series in two-way time that can now be referenced to both the surface seismic data and synthetics from well logs. Now that I've briefly described the flow for the single zero offset source location, let's look at how this expands to include all the offset sources in the 3D VSP. Here's a generalized processing flow used for the signal processing of the 3D VSP source records. Since this really isn't a VSP processing talk, I won't go through each step, but we'll instead look at just a few key details. Let's first take a look at some of the 3D VSP source records. This slide shows 3 separate source points from VSP number 3, each with 3 panels showing the 3 geophone components. These traces have been rotated into a radial transverse vertical orientation, and the graph on top indicates the horizontal distance of each source from the wellhead. I've highlighted the direct arrivals and some of the reflections that I pointed out earlier. This slide shows 3 more source records at longer offsets. A few interesting observations here to point out. Notice the rollover in the direct arrivals, indicating the depth at which the downgoing energy becomes a turning wave and begins heading back up the wellbore. Also, as previously shown by Bob Hardage and others, these P-wave source records show significant downgoing S-wave energy on all 3 components. Also note the very strong mode-converted shear wave reflection at the strawn on the radial component for the source on the far right. To save time, I'll now show you a comparison of a single component before and after this entire signal processing sequence. This slide shows just the raw vertical component for 9 different source locations. And this slide shows those same source locations after all signal processing. Again, the goal of this processing is to isolate and enhance just the P-wave reflections for subsequent imaging and analysis. I'll toggle back and forth a few times so you can see the difference. This flow briefly describes our approach to VSP imaging. Again, I'll spare you the details and just point out that our final product is a 3D image volume in either two-way time or depth that can be directly compared to any surface seismic or well data. In this case, we had some flexibility in choosing our processing grid and decided to match the fine 41¼ foot bin spacing used for the 3D 3C, so our images would line up exactly. As I showed with the zero offset VSP, we now pick the first arrival times for all sources and geophone depths within the 3D VSP survey. This map view shows the travel times from each surface source location to, in this case, the geophone at 4,524 feet. We use these travel times for our upward continuation redatuming process, but they can also provide some insights into any anisotropy present in the velocity field, either VTI or HTI. Here I show a 3D image of a single source and the ray tracing for our upward continuation process. This type of display can give the processor an idea of the illumination possible for any given source point and target depth. This is the result of this imaging process for VSP number 2. This slide shows 3 extracted inlines from the 3D image volume, roughly 620 feet apart. The yellow line represents the location of the downhole geophone array. The illumination radius near the bottom of the VSP array is roughly 5,000 feet. So, now that we've established a little background for the acquisition and processing of these data, I'd like to conclude this presentation by sharing some of our analysis results and insights we've uncovered along the way. This is a list summarizing the type of VSP data used, the data we obtained, and some suggestions on how these data may contribute to the processing of this and other surface seismic surveys. I'll step through these briefly and show some of the results. First, let's look at what basic but important information we obtained from the zero offset VSPs. While this type of analysis is not at all new, I think it's always worthwhile to review and point out the value of this information. The first, and maybe most obvious, is the direct measurement of the one-way travel times versus depth. In areas where well ties are not obvious and surface seismic may be noisy, this type of information is invaluable. Along with the travel times, we can derive a fairly detailed estimate of the vertical interval velocity at each location. And unlike sonic logs, this measurement is from surface and at roughly the same frequency range as the surface seismic, so it can be extremely useful in guiding the processing and imaging of the surface seismic. And since we were fortunate to also have shearwave sources, we were able to get shearwave travel time and velocity information, and then combine that with the P-wave information to provide a valuable VPVS measurement. This is critical information for mode-converted PS wave processing and event registration. Here's the results obtained from the VSP number 2 survey. The P-wave travel times and velocities are shown in red, while the shearwave inline and crossline values are shown in green and yellow. Combining the two data sets gives us the VPVS information in the right panel that we can use for PS wave processing and interpretation. Next, we'll quickly revisit the corridor stacks. To reiterate, this is considered a high signal, primary only measurement of the reflectivity series. In this study, we have both P and S wave data, which we can also use for more advanced multiple analysis. Here I show a comparison of the 3 different corridor stacks at the VSP number 2 location, all displayed in depth. The zoom on the right shows a good tie between the PP and SS traces at the Strawn and below, but some significant differences in the section above that. We're still investigating these variations and eventually hope to compare this to the PS wave images from the 3D 3C survey. And as I mentioned, we can use the zero offset VSP to look a little closer at possible multiple contamination. To do this, we can apply different mutes to the data prior to stacking. This narrow mute is the conventional corridor stack mute intended to pass only primary reflection energy. This deeper mute passes more of the later arriving energy, which may contain interbed multiples. If we stack this, we can consider this a primary plus multiple stack. I'll point out one event here at the bottom that does not continue to the right, implying that it may be a multiple related to the Strawn interface. And while a detailed analysis of the entire wave field shown on the previous slide may be more informative, a simple stack with the 2 mutes and then differencing can point out areas where multiple contamination may be an issue. Here I show the possible multiple arrival from the previous slide that does not show up on the primary only corridor stack on the left of each panel. Let's move on and now take a look at the source wavelet. Since we have geophone measurements at various depths, we can get a good estimate of what seismic energy is actually reaching our key zones. The sweep used for this and the surface seismic spanned 2 to 90 Hz with a low dwell. This low dwell is apparent on the instantaneous frequency display over the first 4 seconds. Let's see how this looks in the subsurface. This is an average amplitude spectrum for the shallowest array setting at VSP number 2. The sweep band is shown by the blue arrow at the top. Unfortunately, we don't see much from 2 to 20 Hz, but on the positive side, we are seeing almost all of the 90 Hz on the high end. This slide shows the spectrum for the middle tool setting. We see the same roll-off starting at 15 to 20 Hz. And this slide shows the deepest tool setting. Again, we don't really see the low frequencies we were hoping for, and now we're also seeing the attenuation on the high side that we might expect at these depths. More on that shortly. And we don't think this is a local effect since we also see this same type of response at the other 2 VSP locations. So now let's look at the high frequencies and our attenuation measurements. This slide summarizes the spectral ratio method we use to estimate Q at each of the VSP locations. This approach has been widely used and provides good estimates for depth varying Q values over the entire wellbore. The graph on the right shows the interval Q values for VSP number 2. We performed this same analysis at the other 2 VSP locations and obtained this comparison graph. As you can see, values of Q range from 20 to 100 for all 3 wells. However, notice the difference in the shape of the curves from the south, the blue and red curves, to the north, the green curve. possibly indicating that a spatially variable Q might be appropriate for this survey. But those that have processed land seismic data know that both depth and spatially variant Q compensation can be tricky and may induce more problems than it fixes, especially related to phase stability. This is an area of active discussion with the surface seismic processors. Next, let's consider the value of shear wave source VSPs and investigate their use for potential shear wave splitting analysis. For VSPs number 2 and number 3, we were fortunate to get shear wave source data, which allowed us to create this 4C corridor stack display on the left. Here I show the results from VSP number 2. From left to right, we have the S11 component with source motion and geophones roughly pointing west-northwest, followed by the two off-diagonal components and the orthogonal S22 component. The middle panel shows the results of incremental 4C rotations from 0 to 180 degrees and the cross correlations of the S11 and S22 components over the deeper section. At this location in the south, we see a fast direction of roughly north 60 degrees east, but with a very small time delay that equates to a percent anisotropy of only around 0.4%. At VSP number 3 to the far north, we see a slightly different orientation, but still a relatively small amount of anisotropy. Now let's take a look at the final P-wave VSP images and how they compare to the most recent version of the 3D survey. This slide shows the 3D VSP image at well number 2 spliced into the preliminary surface 3D volume. Note that the 3D surface image is still preliminary and has some post-stack enhancement applied to improve the continuity and frequency content. The graph on top shows the distance of each trace from the wellhead. And here's the equivalent surface seismic image. I'll toggle back and forth a few times to compare. And here's the VSP image in the deeper section. And this is the surface seismic. Now let's look at the same comparisons at VSP number 1. This display is the shallow section from 600 to 1200 milliseconds. And this is the surface seismic image at that same location. And this is the VSP image in the deeper section from 1200 to 1800 milliseconds. And here is the equivalent surface seismic. This is a good time to point out a difference we observed between the two images, here at about 1420 milliseconds. We're still investigating this, but speculate that it may be a multiple or mode conversion in the surface data that's not present in the VSP image. And finally, let's take a look at the PS wave image from VSP number 2. Here we see the PSV or radial image at VSP number 2. You may notice that the illumination is reduced laterally, which is expected due to the asymmetric ray paths of the mode converted shear waves, which moves the reflection points closer to the receivers in the wellbore. And for reference, here's the equivalent P-wave image from earlier registered in depth. With this image, we now have something to compare to the PS wave data that we hope to get from the processing of the surface seismic data. And to look forward a bit, I've expanded this list with some ideas on what additional information we might extract from this comprehensive data set. This might include a more detailed look at anisotropy, as well as a focused study of specific interfaces for AVO analysis and full waveform inversion. I'm sure there are others that we haven't even thought of yet. So to summarize, we acquired and processed 3 3D VSP surveys in the Permian Basin to help with the processing and interpretation of a new 3D 3C survey in the same area. This extensive borehole seismic data set has provided us with time depth information, seismic scale velocities, far field source information, high resolution reflectivity images, attenuation estimates, multiple arrival information, and shear wave splitting estimates. We look forward to continuing this work to understand the full value of this VSP information as the processing of the surface 3D 3C moves forward. Thank you for your attention.